Hi everybody, this is Mechanical Engineering by Hand, and in this video I'll talk about pipe head loss with natural gas. And so we have a supply of natural gas at 2 psig, which is typical from a meter, and 68 degrees, and then the ambient or the atmospheric pressure is 12.6 psi. So we're up at a certain elevation. And then the pipe is 1/2 inch, schedule 40. There's 200 feet of it with 10 elbows, which have an equivalent length of 36 feet. And then the unit that requires the gas requires 50,000 BTUs per hour at 7 inches of water, which is equal to 0.25 psi. So, and typically we'll have a pressure regulator just upstream of the equipment to control that pressure. So what we'll do is see if we have enough pressure. You would definitely want this much pressure, at least, probably in real life, probably at least 1 psi along this pipe. So we'll see what the head loss is. And then over here, I just took the equivalent length of the pipe, which is 200 feet plus the 36 feet for the elbows. ID of the pipe in feet, the area in feet squared. And then natural gas is mostly methane, which is CH4. And so that molecular weight would be 16. That's 12 for carbon and 1 for each hydrogen. And then the gas constant for natural gas would be the universal gas constant, which is 1545 divided by the molecular weight, and we get 96.6. So the first thing we need to look at is natural gas at this elevation. Natural gas typically has 1,000 BTUs per cubic foot at sea level. But when this gas is discharged from the pipe and into the burner in this equipment, it's going to go to this atmospheric pressure of 12.6 psia. So you need to derate the lower heating value of this natural gas based on that lower pressure. So what we do is just multiply that times the actual pressure divided by standard pressure, and we get 857 BTUs per cubic foot. Okay, so now we know that we know how much gas that requires. So the 50,000 BTUs per hour divided by 857 is 58.3 standard cubic feet per hour. Okay, and then I'm going to jump over here a little bit. We need to figure out the required mass flow of this natural gas. So 14.7 times 144 times 58.3 equals the mass flow in pounds per hour times 96.6 times 528, and this is just P right here. V equals mRT, and T is in degrees Rankine. So solving for this, we get M equals 2.42 pounds per hour. And then the specific weight of this natural gas is typically 0.6 at sea level or standard conditions. sorry, 0.6 is the specific gravity. So compared to air, it has 60% of the weight per cubic foot. And the standard weight of air is 0.075 pounds per cubic foot. And then we'll adjust that for our local pressure. So 14.6 over 14.7. The 14.6 is 12.6 plus the 2 psig. And that equals 0.0447 pounds per cubic foot. Okay, so now we'll see how many actual cubic feet per hour we need. So we take the 2.42 pounds per hour and divide that by our density, 0.0447 pounds per cubic foot. And that's hours. So these cancel out and we get 54.1. This would be actual cubic feet per hour. And then if we divide that by 3,600, that is 0.015 actual cubic feet per second. Okay, and then we need to calculate the velocity, so that would be our ACFS, 0.015, divided by the area, 0.00211, and that equals 7.1 feet per second. Okay, and then I'm going to look up a friction factor, so I need to calculate the Reynolds number first. That is d diameter velocity over kinematic viscosity. So that is 0.0518 times 7.1. And then I looked up the kinematic viscosity on engineeringtoolbox.com, and that is 1.78 times 10 to the negative 4. And so that equals 2066. Okay, so now we'll go to a Moody chart, and I usually use this book, and we have our 1/2-inch pipe is way up here. Steel pipe would be the diameter divided by 0.0002, which ends up being here, 0.004. And then the Reynolds number is way over here, 2066 actually, but we'll just use that line. And so where those two meet would be right about here. And so that would be one option. That's 0.055. Since we're close to laminar is actually, they say 2,000 or below. I think I've read 2,300 or below, but we can calculate this too. So that would be 64 over 2066. And we'll just compare those two. So the first option we looked at was 0.055, and the other option was 64 over 2066, which is equal to 0.03. So this one would give us a lower head loss value, so I'm going to use this 0.055. And okay, so now we can use this equation to figure the head loss. So that would be 0.055 times 236, that's the length, times 7.1 squared. 2G is 64.4, and the diameter 0.0518, and that equals 196 feet. Okay, so the PSF would be 196 times our specific weight, which is 0.0447. And that equals 8.76 PSF, which is equal to 0.061 PSI, and that equals 1.7 inches of water. Okay, so we started out with 2 PSI and we lost 0.06 PSI. So that means at the end here we'll have 1.94 PSI, so we have plenty of pressure. And another way to check your calculation is to look up these flow tables for natural gas. They're called IFGC table 402.4, and they have different supply pressures and different pipe sizes, and then I think they go by lengths, like every 100 feet, how many cubic feet of natural gas can be pushed through that pipe with a certain head loss. So there you have it. I hope that helps out if you have any problems like this with natural gas. Thanks for watching.